one page. Oh no, this is correct. But control F. What it is opening?
It's going to the next slide instead of.
But how do you make it full screen first?
That's what I was checking.
Open in something else, no? Yeah, Acrobat, right? What is your this thing for Adobe? What is your? It's not free. Okay, done. Okay. All right, welcome everyone. Welcome to the 6th edition of CNI Summer School. Before we get started, maybe a quick intro about the Center for Network Intelligence. So my name is Parimal and I am the convener for the center, and we also have a co-convener, Professor Chandramani Singh. I don't know if he is here or maybe students will be here. Okay, so the center does many things. I think we can switch off the lights on the. So the 4 core activities of the center are core research, applied research and development, teaching and training, and outreach. So the core research. So the core research leads to publications which are which appear at the topmost venues, and these also lead to some policy inputs, and applied R&D leads to policy inputs and proof of concept solutions and demonstrations. So in fact, some of the applied R&D which happened at the center has led to inputs during the times of COVID, also some V2X implementation among many others. We also, what is maybe most interesting for you, maybe the teaching and training and outreach. So we have several courses and labs which are available online. So similar to actually Aditya's course on Markov decision process, we also have several courses which is offered to the center, and you can check out on the course web page. We also have some labs which are freely available for you to experiment with, and we have a lot of lecture videos, and we also conduct faculty development programs. Apart from that, we also have we accept a lot of interns. So if you are interested in working with the center, please look out what are the projects we work on, and feel free to apply. And you can also talk to us during the break. We also offer scholarship to ISC students. Apart from that, we have a very rich outreach program which is basically for knowledge dissemination and community building. So we conduct several workshops and summer school. So this is summer school where you are at. We did a workshop last week, and we do several workshops throughout the year. So if you are interested in knowing more about it, you can go to the CNI web page, and I think there is an email, there is a Google group which you can subscribe to. So then you will be you'll keep getting regular emails about the different kind of events which we conduct. Apart from that, we also support conferences, and we have regular seminars which is quite popular and happens every week. And most of the speakers are on are in person, but some of the speakers are also online. So in fact, we have a seminar tomorrow as well. Professor Aditya Mahajan is going to speak. Okay, so these are some of the projects which the center works on. You can take a look at them at leisure. I mean, this slides are available on the CNI web page. So these are some of the verticals which we work on. Digital health, which is these specifically we are doing it now for cancer screening, and infrastructure for AI and ML, which I am working on, AI safety, cellular infrastructure, and Wi-Fi infrastructure. And this is particularly what some of the projects my research group works on. So I'll just let you take a quick look at them. If you're interested, you can come and talk to us during the breaks. And this is the web page for all the different opportunities we have at CNI. So maybe you can take a picture of the QR code, or you can just go to the web page and take a look at them. Okay, so that's all I wanted to say about CNI. So maybe just introduce the speaker. So it's my pleasure to introduce today's speaker, Professor Aditya Mahajan. He will be delivering 5 days lecture on the model approximation in Markov decision process and partially observable Markov decision processes. Aditya is a professor of electrical and computer engineering at McGill University, Montreal. I don't know how many of you know Montreal. It's one of the prettiest city in Canada. Correct? Yeah. Sorry? North America. Not? North America. Yeah. Oh, thank you. He's people from Vancouver might disagree, but I personally think it's very pretty. Yeah, so he's a member of the McGill Center of Intelligent Machines. Yeah, please. At Mila Quebec AI Institute, International Laboratory for Learning System, and I don't know how to pronounce this group, d'études et de recherche, I don't know. Okay, so he received the BTech degree in electrical engineering from IIT Kanpur and MS and PhD from electrical and computer engineering from University of Michigan Ann Arbor. He has held visiting appointments at University of California Berkeley and University of Paris Saclay. He is senior member of IEEE and member of Professional Engineers Ontario. He currently serves as associate editor of Springer Mathematics of Control Signal Systems. In the past, he has served as an associate editor of IEEE Transaction on Automatic Control, IEEE Control Systems Letter, and IEEE Control System Society Conference Editorial Board. So those of you who do not know, IEEE Transaction on Automatic Control is the most difficult journal to get accepted to. I would agree. And he is the recipient of the 2015 George Axelby Outstanding Paper Award, 2016 NSCRC Discovery Accelerator Award, the 2014 CDC Best Paper Award, and 2016 Nexus Best Student Paper Award as supervisor. So the last two were as supervisor. His principal research interests include decentralized stochastic control, team theory, reinforcement learning, multi-arm bandits, and information theory. So some of these things, you know, like he will teach us today, and for others, you might have to look at his papers or maybe the next edition of summer school. So over to you, Professor Mahajan. Thank you. Let's give him a round of applause to welcome him.
Can everyone hear me? All right. Thank you for the kind introduction. So the purpose of this course is to try to present sort of a way of thinking about deriving approximation results in general in sequential decision making, Markov decision processes, partially observed Markov decision processes. I'm going to start by assuming no background on the material, and we will in sort of today and probably the first lecture tomorrow, I'm going to provide some of the background on the basic results, and from then on we'll start looking at approximation. Just to sort of get a feel of how to pace myself, I just want to get an idea about the background of everyone here. So please raise your hand if you have taken a course in graduate probability. All right. If you've taken a course in convex optimization, okay, in Markov decision processes, and maybe like an advanced course in Markov decision processes or reinforcement learning. All right, so I think the level is going to be reasonable, but at any stage if something is not clear, please feel free to stop and ask questions. Okay, so I'm going to start by looking sort of taking this very I'm not sure of the right way, but the very simplistic view of optimization. So I'm going to say if I have a problem where I'm given a cost function which depends on some action, and I want to minimize this cost function by choosing an action in some action set A. This is a simple one-stage optimization problem. When this cost function is linear and my constraint set is a convex polytope, this converts to a linear program. If my cost function is convex and my set is a convex set, this becomes a convex program, and so on. For the purpose of this course, I'm going to say these problems are conceptually straightforward. Okay? This is not necessarily true, but I'm going to take that view that it's easy to solve this problem. All I have to worry about is computational complexity. Conceptually, it's a straightforward thing. Given a function, I optimize it. So what do we do if my set of possibilities is a discrete set? Okay? I'm just going to enumerate the cost for every possible action and pick the action with the lowest value. So that is straightforward. When A is a continuous variable, we would use some tools from analysis. Probably if it is a convex function, I'll take the derivative, set the derivative to 0, you solve that system of equations in some form to find a solution. Okay? So what happens when I have stochasticity? So let me give a very simple example to start with on what is a stochastic optimization problem. And in this lecture, we'll focus only on systems in which we are making a single decision. Okay. So let's consider, this is again somewhat of a dated example, but let's consider a news vendor. So someone who's at a street corner selling newspapers. At the beginning of the day, he has to go to a place and buy newspapers in bulk. And then during the day, people come to buy newspapers and he will be selling those newspapers. Okay. So he does not know at the beginning of the day, when he has to make a decision to decide how many newspapers to buy, he does not know what the demand is going to be. Okay. He may have been selling newspapers for 10 years, so he kind of knows what is the distribution of demand. But he does not know on that particular day what would be the exact realization of the demand. So how does he decide how many newspapers to buy? Okay. So let me formalize this a little bit. So let's say this is called the news vendor problem. So let's say there is a variable P, which is the price per unit, and there is a variable Q, which is the selling price. And clearly, the problem only makes sense if the selling price is greater than the purchase price per unit. Okay. So I'm going to assume P is strictly less than Q. There are two variables of interest in this problem. One is, which I'll call A. This is the amount of newspapers to buy. And I'll denote by W as the demand. Now, what's happening in this problem is that the newspaper is, the vendor is receiving a profit, which I'll denote by little r of A and W. This depends on how many papers he bought in the beginning and what the demand was, right? And this is going to depend on whether the demand is larger or less than the amount of newspapers the person bought. Okay. So if he bought 5 newspapers and 10 people come to the shop, he can only sell 5. Okay. So I'm going to have two cases. Either the demand was less than A, or I can say less than equal to A, or the demand was greater than A. In both cases, at the beginning of the day, he has to buy a newspaper. So he's going to incur a cost, which will be minus P times A in both cases. But in the first case, he can only sell W newspapers. Okay. So the profit that he gets is QW minus P of A. And if the demand is greater than the number of newspapers that he bought, then the profit that he is going to get is QA. Okay. Now, in order to pose the question of what is the optimal amount of newspapers to buy, if I do not know the demand, I have to make some modeling assumptions. So the most common way to model this is to say, let's say I have, this is a random variable, and I know the probability distribution of this random variable. Okay. In that case, I'm going to assume that my objective is to maximize my reward. Let's say this was over some set, and I'm going to take the average value of my return when W was a random variable according to some distribution. Okay. And I'm assuming here I know W is sampled according to some PMF, let's say mu, and I know what that PMF or PDF or whatever distribution is. Okay. So the key difference from the simple static optimization problem is that I'm still choosing one decision, except that my outcome is not deterministic. There are multiple outcomes, and I have to choose an action which maximizes or minimizes the expected value of some function. Okay. Is this clear? Any questions here? All right. So just to fix ideas, I'm going to start with a caricature version of this problem. Okay. So let's say not necessarily trying to model any realistic system. I just want to present a way of thinking. So I'm going to make some very, very simplistic model. 5 or 10, or this is 5 and 20, sorry. So these are just some arbitrarily chosen numbers at this stage. What I want you to focus on is how to think about this problem. Okay? So I'm going to draw what is called a decision tree. And I'm going to draw it left to right. And there are going to be two types of nodes here. A rectangle, which I'll call a decision node, and a circle, which I'll call a chance node. Decision node is the node where my decision maker or the agent act. Chance node, I'm going to model that nature acts at those nodes, and nature chooses the realization of random variables according to a pre-specified PMF. Okay? So I'm going to model this as, for this particular case, the decision maker acts first at the beginning of the day. He has two alternatives, either to get 10 newspapers or 20 newspapers. I'm going to draw a branch corresponding to each one of this. This is A equals to 10. This is A equals to 20. After this has happened, nature acts. Nature is going to pick 5 or 20 with certain probability. And at the end, I have the outcome of this experiment. Okay? And let's say W equals to 5, W equals to 20. For each one of these outcomes, I know the value of A and I know the value of W. So I can compute what is the realized value of this reward. Okay? So if we do that, we get some numbers. Again, this is just for the sake of completeness. The actual numbers are not important for understanding what is going on. And what I want to do now is draw a parallel between, I'll try to reduce this problem to this static problem. And I want you to think what is the corresponding operation we are doing on this decision tree when I go from this stochastic problem to this deterministic problem. Okay? So the basic principle is the same. This is a optimization problem where I have to optimize over a finite number of alternatives. So conceptually, all I need to do is compute the performance of each alternative and pick the alternative with the best performance. Okay? So I can define Q of A to be the expected value of R of A and W. And then I can say I look at the problem of maximizing over the different choices of A of Q of A. So the mathematical or computational difficulty is in computing the expectation. Once I compute the expectation, I've reduced it to a type of problem which I know how to solve. Okay? So how do I compute the expectation in this tree? Okay? So I can go ahead and do this mathematically. I take the value of R equal to 10 and I write this thing down, but this tree is already telling me how to do that. Okay? So what this is saying is, if I take A equals to 10 here, so let's use this. Let's go to A equals to 10 node. I have two alternatives. This gets chosen with probability 1/4. This gets chosen with probability 3/4. I have outcomes with certain values. So I'll take this subtree and I'll average the values at the leaf nodes of this tree according to the probabilities of these values. Okay? So I'll take, looking at just that tree, I'll say Q of 10 should have been 1/4 times 0 plus 3/4 times 10, which gives me, let's just say 15 by 2, so 7.5. Okay? So the key point is, in order to compute the expectation, I need to average over the values of that random variable. If I write this in this tree as this is a chance node, each of the branches gets chosen with certain probability, I know the value at the end of the branch, I average. Okay? Very, very straightforward thing. I'll do the same thing on the other subtree. Okay? Again, the values here are 1/4 and 3/4. So I should get that Q of 20 is equal to 1/4 times minus 10 plus 3/4 times 20. So this is 50 by 4, so 12.5. I think I'm making a mistake, but yeah, okay, that's it. This is okay. So what I have done now is I took this tree, I started from the end of the tree, and I went up one level. In this case, these happen to be the last but one node, happen to be chance nodes, and on chance nodes, I am doing averaging. Okay? This gives me a new tree. This new tree starts with a decision node. I choose A equals to 10, and if I choose A equals to 10, I get an average value of 7.5. If I choose A equals to 20, I get an average value of 12.5. That's the computation that I did on this tree. Okay? Now I'm in the same setup. I'm going to start from the end of the tree and go one level up. The difference is the last but one node now is a decision node rather than a chance node. So at a decision node, I look at the alternatives and I have the option to pick the best alternative. Okay? So the best will depend on whether I'm doing maximization or minimization. In this case, I'm doing maximization. So I go and I say this alternative is the best alternative. Okay? So if I do not care about computational complexity, this is a very, very easy way to solve the problem. I write out the complete scenario of everything that can happen in the system. The decision maker acts, nature acts, you get bunch of outcomes, and my basic principle is I'm going to be simplifying this tree one level at a time, going backwards from the end of the tree. Whenever I encounter a chance node, so if I have a subtree starting at a chance node, I average the values that are here. If I have a subtree starting with a decision node, I take the maximum or minimum value according to my optimization criteria. Okay? And this tells me two things. One, what my optimal action is. So this is telling me the best thing for me to do is to choose A equals to 20. And it is also telling me what is the expected return that I will get if I choose A equals to 20, which will be this value 12.5. Okay? So everything that I wanted to know about this problem, I can understand from this decision tree. Any questions on this? All right. So I now want to point out why something like this is not sufficient and why we would like to think of approximation. And for doing that, I'm going to take a more elaborate version of this problem and try to get it somewhat to a realistic setting and point out what are the challenges if I want to solve this problem in a realistic setting. Okay? So this was, as I said, this was a caricature because I was assuming actions are only two, demand is only two, and that was just because I wanted to be able to draw this tree completely here. Okay? So what, let me give sort of a slightly realistic version. Let's say I'm going to give a version which is still stylized because I want to do some calculation. So I'm going to assume that my demand was in some, let's say, 0 to b interval. Okay? It was a real number over some interval, and I'm doing a real number rather than discrete just because I want to point out something later on. And therefore, clearly my actions should also depend on only on the same set 0 to b. It never makes sense to buy more than what my maximum demand is. Okay? So if that is the case, what I would have is that Q of A is equal to expectation of R of AW. And now I'm in a setting where I'm going to do the same thing, but I'm in continuous valued random variables. So I'll have to use tools from calculus to solve this problem. The last node thing was computing expectations. So I'm going to compute expectations. Okay? What's going to happen when I want to compute expectations? This is a function which is defined piecewise. So I would have to compute expectations in a piecewise manner. In this expectation, A is fixed and W is a random variable. So I would have a situation where I would say this is going to be some integral if the demand is between 0 to A plus another integral if the demand is between A to capital B. And what I would get here is the first objective, QW minus PA. Let's say this had some density FW, DW to QA minus PA, FW, DW. Okay. Now, in a continuous problem, what we would have to do is I can no longer say pick the best alternative. I would have to use calculus. Right? So I would do, let's compute the derivative of this with respect to A. Now, this is an integration where the limits of integral depend on the variable that I'm integrating with. So I'll use Leibniz rule and do this derivation. I'll set the derivative to 0. I'll check the second derivative. I'll check whether this is greater than or less than 0. And in this case, it ends up being greater than 0. I know this is a convex function. So first order optimality condition is sufficient. And I would find the value of A which solves this. Okay? In the interest of time, I'm not going to do that calculation here. It's simple algebra. What you get is the following, which is somewhat interesting. The optimal decision rule has the property that at the optimal value, the CDF, the cumulative distribution function of my demand, should be equal to 1 minus P divided by Q. Okay. So that means on a practical side, if I had the actual distribution of this thing, I can plot the CDF, whatever the CDF is, and I know what the prices are. Based on the prices, I would compute this number 1 minus P by Q. I'll go here and I'll pick the value of A, which is equal to this, and this tells me what amount of inventory I should buy before doing this. Okay. So if I was just interested in the mathematics of this problem, I can stop here. It's a very, very nice, elegant solution. In principle, I can use it practically in a very nice way. All I have to do is plot the CDF of my demand, know the prices, buying price and selling price, and I know how much goods I should buy. The difficulty is, in the real world, I don't know what is the distribution of demand. Okay? So what would happen in the real world? There are two approaches that I can take. Okay? So what will happen is, I started this by saying, oh, let's say I have this news vendor who has been operating for 10 years, so he knows the distribution of demand. What does that mean formally? I'm saying I have some data set, and this data set has a bunch of values. Okay. This is the demand I have observed in the past 10 years. And I am now going to make a modeling assumption that my demand was coming from some stationary distribution. These are independent samples from the same stationary distribution, and therefore, I have different alternatives now. I can try to estimate the empirical distribution of the demand that I did observe. So I can compute some p hat, which is the PMF of the demand that I have observed. I can pretend that this observed demand is this observed estimate of the distribution of the demand is the true distribution, and I can plug that in my solution, and I can get an answer. Okay. This is something which, if you have seen that in your graduate probability course, this would be called a non-parametric estimation. In fact, in this non-parametric case, I'm not really interested in looking at the PMF of this. I'm interested in finding a point of the cumulative distribution function which is at a certain fraction, at a certain quantile. Right? So in practice, the empirical CDF can be computed by simply sorting this data set and plotting it in a sorted manner, and I go and pick the fractional value which is equal to 1 minus PQ, and that will give me a good estimate of what I want to do. Okay. So this is approach 1, in which I don't make any distribution of my demand. The other type of thing that people do is, depending on the discipline, I can say maybe there's some underlying physics, or maybe there's some underlying reason to model this, but I can say perhaps this guy is in a big city, there are a lot of things which are coming in. Each person decides with some independent probability whether he's going to go and buy a newspaper or not. So maybe it's a reasonable assumption to say my demand is going to be a Poisson distributed random variable. Okay. So I can say normally W is equal to some Poisson with rate theta. And if this is my modeling assumption, I can go back to the formula that I have derived, and I can say what is going to be my optimal decision rule. In the nice thing with Poisson is it's a random variable on the exponential family, so the CDF has a nice exponential variation, and I can compute this nicely from the formulas of the CDF, and what I'm going to get is that A is going to be some closed form function of this parameter theta. Okay. In the notes I derive what this actual thing is, but it's again a simple exercise in algebra that once I know the formula for the CDF distribution, I can solve for what A should be. So if my modeling assumption was that my demand is coming from a Poisson distribution, what I would do then is I'll do a parametric estimation. I'll say, given that I have these many samples from a Poisson distribution, what is my best unbiased estimate of the parameter theta? And sort of, if you take a course which talks about parametric estimation, there are various ways in which we do this, and we'll get a method which computes a theta hat, and I'm going to choose f to be a function of the parameters of my distribution. Okay. So this is kind of the thing that we would do in real life. Now, the question that one is interested in answering in these types of things is, so suppose you are a company which is doing this, and I say, well, here is a news vendor who's selling last 10 years of demand at 10,000 rupees, and there is another news vendor who's selling 6 years of demand at 4,000 rupees. Which data would you buy? Okay. So I want to know what is the value of having a larger data set over a smaller data set. I don't know what the true demand is. I have people who have observed the demand. I can pay them to get some data, but they are giving me different quality of data at different costs. So what I would really need to understand is, if I take a data set of certain size, how good, so what's going to change is as I increase more number of samples, I know from probability theory that at some stage law of large number type things will kick in, or I can do concentration inequalities and whatnot, and I can figure out how good is, let's say, how good of an estimate is theta hat of theta. Okay. What I am interested though is not how good of estimate is theta hat of theta. What I want to know is if I have an estimate of theta which is certain good, how bad I am doing compared to the best that I could have done. What is my degree of suboptimality in choosing a decision based on an inaccurate model. Okay. The difficulty in doing that is I have no way of ever finding out what the accurate model is. Okay. This is not some physics problem where there is some Newton's law that tells me what's going to happen. I have some distribution based on human behavior. There are some modeling things which are done here, but there is nothing as a ground truth, right? Everything is, I'm going to have guarantees which say I'll have models which are accurate to a certain degree. I'm making decisions based on inaccurate models. How well can I do? Okay. So that's the central question that we want to address in order to understand how does the quality of my model affect the quality of my solution that I get. Questions? Yeah. Yes. Yes. So. Mm-hmm. Yes. Yeah. Mm-hmm. Yeah. Yeah. So that's a yeah. No, yeah. So that's a completely valid point, right? So let me rephrase. You said the shape of f. In my opinion, it's not the shape of f. It's the shape of my R function. Okay. So the for the interest of everyone, the point that was made was the quality of approximation guarantees that I can get will depend on features of f. If roughly speaking, if I think f is a features of R, if I think that R is a smooth function, then small changes in my distribution, I can invoke something from continuity, and small changes in my distribution are going to have small changes in the expected value of this thing. If this is a function which is changing very, very fast, then small changes can lead to big changes here. So I would need certain properties of my reward function in order to guarantee how good or bad my approximation is. So that is definitely the case, and the bounds that we are going to derive later in the course will depend on properties of this. Okay. It also depends on the type of approximation that I am doing. Okay. So one of the things is I kind of simplified this by saying I'm estimating the parameter of a Poisson distribution. In reality, I have some true distribution, I have an estimated distribution, and obviously I want to measure some form of distance between these two distributions. Okay. There is not a unique way to measure distances between probability distributions, and choose depending on what metric I place on my probability space, what property I want from R will change. So this is going to be one of the main points that we focus later on. What is the relationship between the choice of metric on my probability space and what features I want from my cost function, which will tell me what the quality of approximation is. There was another question? Same question? Okay, all right. Other questions? Yeah. Yes. So if I had a time varying environment, then that would matter. For the purpose of this example, I'm assuming everything is homogeneous, but clearly if you are selling newspapers, 10-year-old data is completely useless. No one right now buys newspapers, right? So yes, so recency of data matters. But for the purpose of this course, we'll not at all worry about how I go from my data set to to approximate model or samples to an approximate model. I'll assume someone has done that for me. Yeah.
Can I something what is notation? I didn't get why you switched from small w to big W.
So sort of I'm following the standard notation in probability theory where capital letters mean random variables and small letters mean realizations. Okay. So I'm taking an expectation. When I write expectation of some function of little a and capital W, that means little a is fixed and capital W is a random variable, which I'll have to tell you what is the distribution of that random variable for me to take the expectation. Other questions? Yeah. No, I did not say A is greater than. So A is something that I will choose, right? So let's go back to this example. The person who sells me newspaper says you can either buy 10 or 20. That's my only option, right? And my demand is 5 or 20. I don't know what my demand is going to be, but if this guy gave me an option of 30, and I know my demand is 5 and 20, I'll never buy 30. Okay? That's what I'm saying here, that it doesn't make any sense for me to buy more than my demand. But I can buy 20 and the demand could realize to be 5. Right? So I don't know, I cannot guarantee a priori that I'll not buy more newspapers. It's just whether it's worth to waste certain things at the potential of getting a higher return. All right. Let me quickly do one more example just to sort of give a different flavor of the type of settings in which these things arise, and perhaps having different constraints that we get in a different application. Sure, yeah. Let's talk about this at a later stage when we have discussed a bit about the approximation results that we get. But short answer is, if I don't know anything about my model, I can't say anything. So I'll have to make some assumptions before I can say whether something is good or not. All right. So since we are in the microprocessor building, let me give an example from circuits. This is what's happening in modern circuits, which are known as multiprocessor circuits on chips. A small example is, let's say I'm making an IC, and I know that in order for my system to run, it needs, let's say, 1 CPU and 1 RAM. Okay? I want to build a reliable system, and so I decide to over-provision. I say my IC I'll make a bigger circuit, and rather than having only 2 components, I can have 3 components. Okay? So I could either have a CPU, and a RAM, or I could have a CPU, RAM, and RAM. And the way it works is, once I start my system, in this case, 1 CPU and 1 RAM will be used. In this case, 1 CPU and 1 RAM is being used. And as I'm running the system, due to thermal effects and whatnot, at some stage, one of these running components will fail. Okay? I probably have some model on the time to failure of each one of these components. And if one of the components fails, let's say in this case, if the RAM fails, my circuit goes away because I cannot run the system anymore. But if my CPU fails, I can start the next CPU, and now my circuit will run till the second guy is running. Okay? I have the same type of thing here. If the CPU fails, the circuit stops, but if the RAM fails, my circuit could run for a longer time. And the question that I want to ask is, given the distribution of time to failures of these components, which of the designs is better? Okay. So, in terms of modeling, I'm going to say that there are, so what's important when I'm modeling something like this is to separate out what is the source of uncertainty in the system, and then I would construct a cost function or a reward function which captures what is the outcome as a function of that uncertainty. Okay. So, the entire uncertainty in this is going to be measured by the time to failure of these different components. So, I am going to say, let's say W1C is a random variable which tells me how long my first CPU is going to last. W2C is a random variable which tells me how long my second CPU is going to last if that is put in my chip. I have W1R and W2R. Okay. So, there are 4 random variables in my system. This is all of them. And now, once I have something like this, I can easily model the question of which alternative to pick. I'll say for alternative 1, what is my expected cost? So, the expected cost for alternative 1 is going to be equal to, what I want to say is it's going to last to the maximum of W1C plus W2C, sorry, not the maximum, the minimum of W1C and W1R, right. In design 1, whichever happens first causes the circuit to break. Either my RAM breaks down or my first CPU breaks down and then the second CPU breaks down. Okay. And you will do Q of alternative 2 is going to be minimum of W1C, W1R plus W2R. Okay. Now, in case the system model is known, right. So, suppose I assume the lifetime of a circuit component is again an exponentially distributed random variable. Computing, sorry, this is not Q, this is just the total cost. This is, sorry about that, this is cost of, let's call it A1, and W is the collection of all these 4 random variables, and this is the cost of A2 and the collection of these 4 random variables. Yeah. Yeah, this should be rewards. Thanks. I'm maximizing this. Yeah. Okay. So, in principle, if I give you the distribution of these guys, I have the same thing that I can compute the expectations, and it becomes a exercise in basic probability calculations, right. So, but the point is it depends a bit on my modeling assumptions, right. So, if I want my probability calculations to be simple, I can say, well, I am going to assume that this guy breaking down and this guy breaking down are independent random variables. And now I am talking about sum of independent random variables. So, the joint distribution is going to be convolution of the random variables. Depending on what family I pick them from, I can figure out a closed form for the joint distribution and I can do these calculations. Okay. But the challenge is, in reality, I don't know whether these guys are going to be independent random variables or not. Okay. In particular, this is definitely not the case that W1C and W1R are independent random variables, because the reason a circuit breaks down is due to thermal effects. The chip is getting heated together, so there is going to be some correlation between the failure of the first component and the second component. But for the purpose of my mathematical modeling, I don't know what this correlation is. This is some complicated thing. I can make a simple modeling assumption that these guys are independent, and I can get some answers of what is going to happen. But that is a model of reality. My real system is somewhat different. Okay? And I want to understand, if I make this simplifying assumption about the model of reality, that these random variables are independent, but in the real system they are correlated, can I say how good my decision is? Right? And that again boils down to this question, how good, like, so clearly I have to say something about how correlated they are, right? So I'll have to say, given my true distribution of nature, which is some joint distribution over these 4 random variables, and my modeling assumption that these 4 random variables are independent random variables, what is the difference in the circuit lifetime that I get if I choose the solution corresponding to my approximate model in the real system. Okay? So in this case, the model approximation is not necessarily coming because I was not able to model the lifetime of a component well, but there is some interaction between these different variables, and I don't have a good model for that interaction. So in order to have a solvable problem, I make some assumptions, right? And this would be true even if I was not doing this in an analytic way, right? You can say, okay, maybe I'll run Monte Carlo simulations to be able to compute these minimum of this and compute expectations. But the fundamental question remains, even to do Monte Carlo simulations, I need to make some assumptions about the joint distribution of the random variables, and all I have are marginal distributions. Okay? So that's kind of the motivation for trying to understand what happens when I have an approximate model that I'm using to make decisions. Okay? What I want to do next is look at the problem of observations. So far, we assumed that my model was just this static optimization problem. Sorry, just getting there on my notes. Okay. So far my assumption was, look, there is this problem of optimizing some function, and all that we have done in a stochastic optimization problem, so this is deterministic optimization, and stochastic optimization is simply saying I'll minimize or maximize A belonging to some function of A, where this guy is the expectation of cost of A and W. Okay. In lot of applications, we have additional side information. So let me go back to the news vendor problem, and let's say I know that the number of people who are going to buy the newspaper from the shop depend on whether this is a sunny day or a rainy day. More people may be coming when we have a sunny day, less people will be coming when they have a rainy day. Okay? So I'm going to model this by saying that there is an event S which is sunny or rainy, and this event determines the distribution of my demand. So the distribution of my demand was probability of W. Recall that in this example I was taking W takes value in a set which is 5 or 20. So this would be probability W is equal to 5 given sunny, and I'll assume this is the same thing that we had last time, and I need to say what is the probability W equals to 5 when this is rainy, and for simplicity let me say this is 3/4. Okay? And note that W is effectively a binary random variable. I'm specifying one probability, so that is just 1 minus this. That's why I'm not writing it out in detail. So I want to again go back to the decision tree and draw the decision tree corresponding to this. And the key point that I want to keep in mind is that when I'm drawing this decision tree, I will always go in the temporal direction in which the random variables are realized, or in which all the system variables are realized. So what happens in this physical system is the day starts nature determines whether it is sunny or rainy. Let's assume both of these things happen with equal probability. So the first node is a chance node, which decides whether something is sunny or rainy, and I have equal probability for both these events. If it is a sunny day, my decision maker knows that it's a sunny day, and he has to decide how many newspapers to buy. He has to buy either 5 or 10 newspapers. Then it is nature's turn to act again. Nature determines the value of the demand. It's sorry, this was 10 or 20, and nature determines demand, which is 5 and 10, and you get some outcome. And I have the same problem in the rainy day. The decision maker decides whether to buy 10 or 20. Nature decides 5 or 10. The difference now is that the distribution of W's on these final branches depend on what happened here, but I have drawn a complete tree, so I can compute these numbers as a function of which part of the tree I am. Okay? And again, I have more alternatives here because I am considering a more complicated problem. Now, before we go on how to solve it in a simplistic way, let's think of how does the newspaper vendor have to think about this problem the night before. Okay? So the night before, he does not know whether next day is going to be sunny or rainy. All he knows is there's a 50% chance it's going to be a sunny day versus a rainy day. So he needs to come up with a plan. He needs to come up with saying, if it is a sunny day, I'm going to buy X number of newspapers, and if it is a rainy day, I'm going to buy Y number of newspapers. Okay? This thing is known as a policy or a strategy. I'll use the term policy. This is a map from the observations of the decision maker to its actions. Okay? So I'm looking at the problem at this point. This is the ex ante view of the world when nothing has, no random variable has realized. At this stage, I say, look, what I need to do is I need to figure out if I'm in the sunny node, what should I do? Let's say I decide to do this. If I'm in the rainy node, I decide to do this. This is a policy. The policy tells the decision maker at all nodes corresponding to the nodes where the decision maker is acting, all decision nodes in the tree, what action to take. Okay? If I take the view of a policy, conceptually the problem is same as before. Now I have two decision trees, two decision nodes. Each decision node has two outcomes. So there are going to be 4 policies. Either I choose low or high here, low or high here. So 2 cross 2, 4 options. So I can enumerate all 4 policies, pi 1, pi 2, pi 3, pi 4. For each one of these policies, I can compute what I'll call j pi. This is the expected value, in this case, of the reward, which depends on the action that I take, which will be pi of s, the realization of w, and s. In general, the reward could depend on all 3 random variables. And what I know is the joint distribution of w and s. And I want to choose my action as a function of my observation in order to get a reward. And my optimization problem is maximize pi over set of all policies, j of pi. Okay? So if I take this view of enumerating all policies, I am back to a deterministic optimization problem. List all policies, compute the performance, pick the option with the best, pick the policy with the best performance. The drawback is this guy. Okay? So in my original problem, I was optimizing over actions. So this was a parameter optimization problem. I'm picking, let's say, a real number. Right? What happens to the number of policies? If my policies are maps from state to actions, the cardinality of the number of policies is the number of actions raised to the power of number of states. Right? So the number of policies, it just seemed to be 4 because I have constructed this very, very simple example. But if I go to, let's say, the example we were considering last time, that I have a demand with some support, this is going to be a humongous number of alternatives. In continuous variables, this is an uncountable set. Okay? So I have now a computational difficulty. Conceptually, I could just go to a parameter optimization problem, enumerate all policies, find the policy with the best performance, but this is going to become computationally impractical very, very soon. So I want to come up with a scheme which does not suffer from this exponential complexity in the size of my state space, in the size of my observation space in this example. Okay. Is it clear what the concern is? Okay. So how do I solve this? Okay. Any ideas? Can just use what we did last time. Okay. So it takes a bit of a conceptual leap to understand what's going on. So rather than thinking about this decision maker the night before, suppose the decision maker comes up with the following plan. Says, I'm not going to do any planning right now. I'm going to wake up tomorrow. I'll see whether this is sunny or rainy. Okay. If it is sunny tomorrow, I'm in this part of my decision tree. I already know how to solve this. Okay. So if it is sunny, I'll follow this procedure, going backwards over this, averaging over the chance nodes, optimizing over the decision nodes, and I'll figure out what the optimal action is. If I wake up and it was rainy, I'm just going to look at this part of my tree, and I'm going to do the optimization the same day. Okay. Therefore, if I do have to make a decision the night before, I can do the following. I can say, let me imagine that if I wake up tomorrow and it is sunny, I'm going to solve this problem, and I'll store the solution. I'll imagine that if it is rainy, I'll solve this problem, I'll store the solution. I combine both of those solutions, and I get what I have to do if it was. I can find the entire policy at the beginning of time. Okay. So let's write down what this means for the purpose of this example, and we'll see that we have now an algorithm to solve this problem. So what I'm going to do is exactly the same thing we did last time. Let me look at this tree. What we did last time was I started at this node, and I computed this function which was some function of this section and some function of this section. I'm going to do the same thing again here. The difference is going to be that this node, when I'm doing the averaging, it does not depend on this. It also depends on what happened before that. So at the last but one layer, I'm going to compute a function which I'll call Q of S and A. And this is going to be the expectation of, in this problem, R of A, W, and S, conditioned on big S is equal to little s. Okay. So notice in the model that we are considering, whether it is sunny or rainy actually does not affect my reward. All it does is affects the distribution of my demand. Okay. So what I'm saying is, if I am at this part of my subtree, the probability of these two guys will depend on the fact that it was sunny. Okay. So I have given some numbers for this, so I'm going to compute that averaging here. So in the tree, I had already written down what were the probabilities of this, and when I write down these probabilities in this tree, that's automatically conditioned on the fact that it is sunny. I average according to those numbers, and I get a value for these two nodes. Okay. So what will happen is when I do this reduction is that I get the following tree. And I'll have 4 different numbers here. Okay. I'm not doing the actual calculation, but sort of it should be clear at this stage how I'm going to be computing all these 4 numbers. And now I'll follow the next step again. I'm going to call this Q star. And the purpose of the star will become clear in a bit. I'm going to now do the same thing and go back again. So I'm going to go to this decision node, and I'll say I have 2 alternatives. Alternative A equals to 10 gives me Q of Sunny and 10, and this guy gives me Q of Sunny and 20. I've computed these numbers. And at this stage, I'll choose the branch which has the higher number, right? And the Sunny part is same as last time, so this is going to be this branch. I'll do similar calculation for the other side, and I've chosen these numbers in such a way that this guy turns out to be this branch. Okay. So what I get now, I'm getting 2 things out of this calculation. I'm getting a value for this node, which I'll say is V star of S, which is maximization over all A of Q star of SA. And the second thing that I'm getting is pi star of S, which is the option which maximized this value. Okay. Just a minor technical comment. I wrote this as equality, but argmax is a set valued function. It is possible both of these had the same value. In that case, it does not matter which option I pick, they are going to have the same performance. So normally when I'm writing this rather than equality, I'm going to write this as any element in that set. Okay. If I have multiple optimizers, for my purpose, it does not matter which optimizer I'm picking. Okay. Once I've done this, I get a reduced node where I have V star of Sunny and V star of Rainy, and I have the probabilities of these 2 things. So to complete my methodology, I need to go back one more step and compute the average value at this node. Okay. And what I get is that the optimal performance is going to be the expectation of V star of S. Okay. So is the procedure clear to everyone? Did the policy that I find, is that optimal? How do I prove that it is optimal? Okay. So there is one way of thinking about proving optimality in these settings, and that is the following. Let me go back to this tree and think of any policy on this tree. Okay. Any policy is going to be, I look at these decision nodes and I'll tell you what things to do on this decision node, right? Which action am I picking on this decision node? So how will my, can I compute the performance of that policy using the same backward procedure on this decision node? What I'm going to do is, suppose I gave you a policy where, let's say, just to get a different thing, both were choosing the high value of goods to buy. So what I'll do is, the last state is going to be the same. I'll do this averaging over chance nodes. Whenever I have chance nodes, I'll do averaging. What will differ is, how am I getting a value at my decision nodes? I'm no longer doing the maximization. What I would be doing instead is I'll call this guy q pi of S and A. In this case, it happens to be the same. As we go forward, we'll see that this is no longer the case. Reward of A, W conditioned on S equals to little s. I'm going to compute now V pi of S, the performance of policy S on that subtree, and this is going to be equal to Q of S and pi of S. Okay? Because I did not necessarily pick the optimal action, I chose the action specified by this policy. Okay? And the last step is going to be the same. J of pi is going to be the expectation of V pi of S. Okay? Now, in order to show that the policy that I get is optimal, I'm going to, okay, so slight mismatch. This example is for maximization. I'll focus on all my proofs for minimization. So let's assume we were solving a minimization problem and Q stars and V stars were solved by minimization, just because sort of we have to fix one convention in order to do proof. So the idea is very, very, very simple. Okay? So I'm going to make the following claim. First, I'll say in the minimization setting, Q star of SA is less than equal to Q pi of SA for all pi and for all SA. In this particular setting, this is obvious because what was happening at the last time, there is no optimization happening. I'm just doing averaging over this. Q star and Q pi have exactly the same definitions. Okay? So this is equal trivially in this example, that in the one-stage problem, these two guys are equal. Then I claim V star of S is going to be less than equal to V pi of S for all pi, for all S. Okay? This is true because I was doing optimality at this thing, and I'm just arbitrarily picking an action at the other step. So by definition of optimization, V star of S is less than equal to any other policy at S. Okay? I have another part that V star of S is actually equal to V pi star of S. The policy that I picked, which was always the argmax that I took, that clearly should be equal to this, right? This is the definition of argmax. Argmax says pick the alternative. So if I have two branches, I say pick the branch with the higher value, and I'm saying if I had picked the branch with the higher value, that is better than any other branch that I should have picked. That is equal to the best branch that I would have picked. Yeah. In this case, it does not, but I'm following this notation because when we'll go to multi-stage problems, we will see that this depends on pi. So that's why I said in this case, Q pi is same as Q star, but when we go to more complicated problems, this would be there, and I want to say that the proof idea remains the same. Okay? All right? So once I have these two, I take the expectation. So what I have argued is essentially V pi star of S is less than equal to V pi of S for all pi and for all S. Right? That's just combining these two statements. So if I take the expectation over the distribution of S, I'll get that J pi star is less than equal to J pi for all pi. Therefore, pi star is an optimal policy. Okay? So this is somewhat trivial in this case, but once we understand this, when we go to multi-step problems, it's going to be the same solution. Any questions on this? Yes. Agreed. I am not talking about efficiency at all. Okay. Yeah, but you cannot. I mean, this is lazy evaluation, right? So what you are saying is, I did not have to compute the policy because if it was sunny tomorrow, I didn't need to know what I would do when it is rainy. Okay. That is true if I had the ability to do the calculation the next day, right? Suppose this was a more complicated system. I needed to run a computer simulation to figure out what the optimal answer is. I can't go tomorrow and start opening my laptop and running a simulation. It was something which took time, right? So in that case, I would need to pre-compute the policy. So it depends on that, but yes, there are situations where I can do this in an online manner and not necessarily have to pre-compute everything, but we'll not worry about that for the purpose of this course. We'll get to that when we go to multi-stage, okay? There's one more thing I want to convey before we finish this lecture, which is somehow the most important feature that I want you to understand. So how do we, what I said was, well, if I had side information, I can sort of have to compute this Q function as a function of a side information and actions, and then I do the optimization for every realization of this side information. What if my side information is useless? Okay. So suppose I am a superstitious news vendor, and I say, look, I'm also going to keep track of whether I woke up on the right side of my bed or the left side of my bed. Okay. I believe that has an impact, but the actual demand distribution just depends on whether it is sunny or rainy. It does not matter where I woke up. That has no impact on how many customers are going to come to buy this. Okay. But I want to model it by saying I believe left or right has an importance. Okay. What am I going to do? I'll still build a tree. What will happen in this tree is, let's see how I did it in my notes. Okay. So what I'll say is, at the beginning of the day, nature decides whether it is sunny and which side of the bed I wake up from. Okay. And let's assume we have some joint distribution over all this. So I'll have 4 possibilities. This is rainy and right side, rainy and left side, sunny and right side, sunny and left side. Okay. I have now 4 decision nodes. I need to decide what to do for each one of these cases. I will either buy low or buy high, and then I'm going to have 8 chance nodes, and now nature decides whether the demand is low or high. And I can go back and do this entire calculation that I described on this. I go to all these nodes, compute these numbers. What is going to happen when I compute these numbers? My assumption is the news vendor waking up on the left or right has no impact on the distribution of the realization of demand at these nodes. Okay. So what I computed here would be Q of S, Y, and A, and that at this node and this node are the same. Right? That means that, sorry, that at this node and this node are the same. That when I average over, these are the same S values and the same A values, A equals to 10. These are the same S and A values, but these are different values of which side of the bed I woke up. I'm going to call that with y. There are different y values, but this and this expectation is the same. Right? Same thing will be true for these two nodes, and these two nodes. Okay? What that means is that when I look at now this subtree and this subtree, this is tree 1 and this is tree 2. Tree 1 and tree 2 are identical. Okay? Because the information that I had access to was irrelevant. So what I'm saying is, if I compute Q of S, Y, and A to be expectation of, and just for consistency of notation, I'll switch back to a cost thing just because I want to do a proof. I'll say this was a cost which depended on S, A, and W. Y does not impact the cost, but or in this case even A does not affect the cost. I have a cost of A and W, S is equal to S, Y is equal to little y. Okay? And the claim is that if Y is completely independent of S and W, I just have some completely garbage information, this expectation is not going to depend on Y. So if I take any two F values, Q of S, Y1 and A is going to be equal to Q of S, Y2 and A for any Y1 and Y2 which belongs to this set Y. Okay? Therefore, when I get to this node and this node, my decision is going to be the same. Okay? So rather than choosing a policy, so I was saying, look, my policy should have been a function from my whether it is sunny or rainy to whether I woke up from left and right to how much should I buy. It turns out that the optimal policy will have the property that pi star of S and Y1 is equal to pi star of S and Y2. Okay? So if I have garbage information, it does not help me in making decisions, which makes sense. But the interesting thing is, this is also true if my information was not completely garbage. Okay? So I deliberately started with an example where I said that the additional information that I have is something completely irrelevant to my problem. But if I look at the proof, what I really used was the fact that if I look at the distribution of W conditioned on S, that should be independent of Y. So Y can be something which has information about W. As long as it is conditionally independent on S, I am okay. So if my news vendor has, I don't know, he has a barometer, he measures the pressure at the beginning of the day, clearly that is something that is related to whether it's going to be sunny or rainy, but any information that the barometer reading provides about the distribution of the demand is already captured on observing whether it is sunny or rainy. So it's not providing any additional information. So this result is known as Blackwell's principle of irrelevant information. And this is saying that if I have a problem where my cost is a function of S cross A cross W to R, and I have access to a random variable Y such that let's say Y is independent of W conditioned on S. Okay. Then there is no loss of optimality in choosing A just as a function of S. So I can ignore y while making my decision. So this tells me when is information that is available to us, when is that irrelevant for the purpose of making decisions, and that is the case if I have access to other information such that this information y is conditionally independent of all my payoff relevant variables conditioned on S. And the proof is exactly the same. All I did here was to argue that this conditional expectation does not depend on y, and therefore the corresponding q values will be the same, and therefore the corresponding policies will be the same. Okay? This is going to be the backbone result on which we will develop simplification of this basic algorithm when we go to multi-stage problems. Yeah. Mm-hmm. Yeah. No, this is something much simpler, right? All I'm saying is this is really a mathematical statement about conditional distributions. Under this condition, if I go through this procedure of doing policy computations, this information is not helping me make a decision. Yeah. So it's in the minimizer case, I'd erase that. Pi star will be defined as the argmin of the Q function. Yeah, so I'm doing all my proofs for the minimization setting. Yeah, so all the proofs are going to be in minimization. In examples, I'll choose minimization and maximization depending on what makes more sense for the problem. For almost all problems, it does not make a difference whether we are doing minimization or maximization. At least whatever we'll do in this course, it doesn't make any difference whether we are doing minimization or maximization. There's some results in Markov decision theory where it makes a difference, but we'll not touch upon those. Other questions? All right, if not, then I think this is a good time to stop, and we'll reconvene in half an hour.
So, sorry guys, so we're going to take a picture in front of the EC main building. We'll have people guiding you there, and then we'll come back in half an hour. So those of you who have not registered, please do so now. The online registration form is open. This is very important, yeah?
Welcome back, everyone. So I'll start with a quick recap of the basic ideas that we saw in the previous lecture, and we'll build up on this, right? So in the case of discrete valued random variables, this is the generic form of my one-stage optimization problem. Something happens in the world. I could have different, let me draw multiple this, different things which are happening. This is what I was calling F in the previous lecture. The decision maker observes what has happened in the world. Based on that, it has to choose an action, and these were the different possibilities of the actions that the decision maker chooses. And then something happens in nature, and we have different outcomes based on that. And I'm giving you a cost function or a reward function which says what is going to be a cost or reward at all these terminal nodes. Okay? So the terminology that I'm going to use from this time onwards is that this is a trajectory, and the final node of the trajectory is an outcome. And essentially the one-step stochastic optimization problem is nature acts, decision maker acts, nature acts, we have an outcome, I give you a reward function or a cost function which depends on the outcome, and I want to optimize that. And the basic algorithm that we have is going backward from here. So what I'm going to do is I can represent each node here as indexed by what has happened so far. So the node at the decision maker time is indexed by what happened in the first move of nature. Nodes at this level will be indexed by what happened at S and what action did the decision maker take. And the final nodes would be what happened in the beginning, what action did it take, and what was the realization of the uncertainty. And our assumption is I have a cost function which depends on S, A, and W in the most general set. And we do the following computations. I compute Q star of SA. So at each of the penultimate node here, I compute the expectation of C of S, A, and W, and I'm going to write in its most generic setting now that S is equal to little s and A is equal to little a, allowing for the possibility that the distribution of W may depend on the action that I take as well. Okay? And so this is the averaging done at the chance node, and I do optimization at the decision node. I compute V star of S to be minimization of Q star of S and A, and my optimal policy is something which chooses one of the argmins of this guy. Now, one thing which I did not explicitly mention, it's worthwhile checking what does this decomposition give me compared to the brute force search. So recall that the brute force search was enumerating all policies, and I do compute J pi and minimize this over all pi in the set of policies, and the number of policies that I would have is the number of maps from the set S to the set A, which will be A to the power of S. What am I doing here instead? I'm computing this Q function, Q star of SA, and this requires complexity which is proportional to number of values of S and number of values of A, and then I do an optimization here. Okay? So the overall complexity of this is proportional to S times A. Okay? So I have gone from something which was exponential in my number of observations to something which is linear in my number of observations. And this is the big simplification that I want to maintain in the multi-stage setting. Okay? The second part, which I talked about having this irrelevant information, I am now going to interpret that differently. So if I fix with this notation the example that I gave of the news vendor knowing whether it is sunny or rainy and knowing whether he gets out from the left side or the right side of the bed, these are just two different values of the complete observations that he can get. And what I'm saying is that suppose the following was true. If I have some function which takes my set of observations and gives me something smaller, let me call that S hat. Okay. I go to a smaller set. In my example, it was looking at the whether it is sunny or rainy, looking at the weather and looking at the side of the bed I got off, and I'm just keeping the first component. But this could be any function which compresses information, which has the following property, that if sigma of S1 is equal to sigma of S2, that implies Q of S1 and A is equal to Q of S2 and A for all A. Okay. This was the case which happened in our last example. If I ignored which side of the bed I got off, that gave me the same performance irrespective of what action I took, right? Those two subtrees were the same. So if I have that, Blackwell's principle of irrelevant information says that I'll use this without loss of optimality. I can choose pi star simply as a function of sigma of S. Okay. So this gives me a way to characterize when can I take decisions based on less amount of data than I may have, and that is as long as it does not affect my these Q functions. Okay. If I can compress my past information in such a way that it does not affect my evaluation of the future cost, then I don't need to know which of these things that I'm in. I can just store a compressed value of that. Okay. What I want to do now is take these two basic ideas, having a procedure which reduces exponential complexity to linear complexity, and having a procedure which tells me when can I compress information, to come up with an algorithm for the multi-step case. Okay. So again, let's start with a simple example for the multi-step case. Yeah, sure.
So in the newspaper vendor problem,
Yeah.
suppose the newspaper vendor also has to dispose of the unsold newspaper.
Okay.
So he may not want the unsold newspapers at the end of the day to exceed a level, let's say U, with probability more than alpha.
Okay.
Now it's not clear whether there will be an optimal policy of the type that you have, deterministic policy.
Okay.
Or say if he wants his long time expected unsold newspapers to be within, say, some threshold lambda.
Okay.
Right now he cannot ignore the weather distribution.
So so let me paraphrase. If I have a constraint, then I'm implicitly making an assumption here that I can restrict attention to deterministic policies. If I have constraints, I will have to look at stochastic policies. The view that in case of approximation, it is not trivial, but in the case of optimization, the view that I'll take for the purpose of this course is that it does not matter if I have sufficient regularity in my problem. I need to look at a Lagrange relaxation, and whatever I'm doing will be valid for Lagrange relaxation. Okay? But yes, I mean, as you know, right? So if I have to solve a constraint problem, I cannot do just single dynamic programming. I'll have to do something slightly more intelligent. But for the purpose of this course, we'll ignore that completely. Just in terms of all the policy evaluation formulas, nothing really changes if I have a stochastic policy. I just need to average over that. It just becomes notationally heavier, and that's why I'm restricting to deterministic policies. Okay. Yes. Yes. Yes, it will be the number of state and actions that I have. It's not exponential, right? I have f states. For every state, I have a actions. So it is f times a. Okay? While the number of policies were saying, what do I pick for everything? So that is the number of functions from f to a. But here I'm just computing one function for every realization of s and a. Okay? Yeah.
So I think in the last lecture you ended by proving that my star is actually the actual quantity.
Yes. Yeah.
What's going on here? Like there's intuition, but why in my interpretation is kind of greedy.
Yes, it is greedy because in this case, right, I computed the conditional, given my current information, I computed the conditional expectation over all future random variables. So this, I can be greedy with respect to that, and that will be my optimal policy. It will become slightly clearer when I go to multi-stage problem. So just wait about half an hour. Okay? All right, so let's look at multi-stage setting. And I'm going to start with a simple model. We'll try to understand what happens there, and then we'll go to the more generic mathematical model and translate our steps to that model. So I'll look at a slight variation of the inventory management, of the new vendor problem, which is called inventory management. So let's assume you are a big online retailer like Amazon, and I'm only talking about one product. Okay? So Amazon has an option of keeping certain amount of, so they know what type of demand they get. Let's say they're selling markers. Okay? So they're going to keep certain amount of markers in their warehouse, so that if you go online and buy a marker, they can immediately ship it to you. But they don't want to store a huge number of markers because there is a cost involved in storing them. Their warehouse has finite capacity. If you're storing more markers, there's something else that you'll have to not store. But if you have too few of a markers in your store and someone places an order, you'll only be able to fulfill it in the future. Right? So you'll not be able to deliver it the next day. You'll say maybe wait 2 days, we'll have to buy it from our supplier, and then we'll give it to you. Okay? So what I'm going to assume is that there is a stock level Ft of some stock. So the number of markers that they are in the store. And I'll take a rather simplistic view of this problem just to keep things tractable. I'll say at the beginning of the day, Amazon can go and place an order of certain number of markers from its supplier, and the supplier delivers it instantaneously. In real world, there's going to be some lag, makes modeling a bit more complicated. So let's simplify and say these are delivered instantaneously. During the day, there is some demand. Okay? If the demand is less than the amount of stock that the seller has, you can just fulfill the demand. But if the demand is larger, your demand gets backlogged. So I don't lose the customers. I say I can fulfill this demand in the future, but it's a risky thing because the customers may not wait till the future. Some fraction of them may decide to go to some other buyer. So you want to avoid having too large of a backlog. Okay? So I'll assume that there is dynamics here, that the stock at day t plus 1 is the stock at day t plus the amount of goods that I procured at the beginning of the day minus the demand that got realized during the day. Okay? And I'm going to say that I have two costs. There is a cost, P is the cost per unit good. So if I place a order for A items, I have to pay P times A. In addition, I have a holding cost. And the holding cost depends on whether my inventory level is positive or negative. So I'm going to make the following assumption, that I have a holding cost H of S, which has this shape. This is again sort of just to simplify the analysis. I have a holding cost which is linear in the positive side and linear when I have negative. So some type of a weighted absolute value function, if you want to think of that. And it's more expensive for me to be backlogged than to have more goods in my warehouse, right? Because here I'm just competing with space with other goods. Here I can lose some customer. And I look at this problem over a 2-time period. And for simplicity, I'll say in the example that I'm giving, there are 2 values of A that I can pick, and there are 2 values of W that can be realized. Okay? And the details are given in the notes, and actually the notes are, the site is written here. There's a course notes accompanying the course, and you can go to the registration website of the course and get it, or you can read the link from here. But my model is going to be the following. At the beginning of time, this is a decision node, and I'm going to assume that we start with 0 amount of stock in the warehouse, just for simplicity. And the decision maker has options to either buy low stock or buy high stock. Let's assume there are some numbers. We don't really care about the details, but I want to expose what structure we will get here. Depending on what you buy, now it is nature's move, and nature determines what is going to be the realization of the demand. Okay? So let's say nature determines low demand or high demand. And this is now the end of day 1. Day 2 happens, and the same problem repeats. Now, depending on what happened here, either the decision maker placed a low order or a high order, the demand was low or high, you have to decide. There are 4 possibilities, and I need to decide what to do in each one of these possibilities. Yes, I'm assuming demand can drive it negative, and I'll have to pay a cost which will be proportional to whatever this slope is. Now, I do the same thing. I do either low or high. Then nature X chooses low or high, and so on. Okay? So now what has happened is my decision tree has become deeper. My decision maker has to make 2 decisions instead of 1, and the number of terminal nodes have increased. Okay? And depending on the value of P and this H, here I will incur a cost, which will be, I have to pay a cost of how much I ordered on day 1, plus a cost of how much I ordered on day 2, plus a holding cost on what was the amount of goods that I had at the end of day 2. Okay? Let's say there is no other cost after that. Okay? So again, given the trajectory of realization of all variables, this is something that I can compute. So I'll have numbers at the leaf nodes everywhere. So now our definition of a policy has changed. So you see, the policy now, my decision maker has to make decisions in 2 nodes, have to make decisions here and here. And in these 2 nodes, I now have a policy, right? So I need to decide what to do here, either this guy or the other guy, and in all of these, I have to decide what to do. If I tell you what the decision maker does at every node at which it has to act, that gives me a policy. So my definition of policy is same as what we did last time, but the difference now is that the decision maker is not acting at a single time. It is making decisions at 2 different times. Okay? And again, I can solve this in a brute force manner. For every policy, I can compute j of pi, and then I want to do minimization over all pi in capital Pi, j of pi. Okay? The difficulty is going to be the number of policies. See, at the first stage, I only have 2 actions, but now I have 2, 2, 2, and 2 actions. So the number of policies are 2 to the power of 1, 2, 3, 4, 5. Right? So I have 32 policies now. If I go to a 3rd time step, I'll have binary options in all of those nodes. So it's something which is going to increase exponentially over time. Okay? So the challenge now is, although conceptually I can just do this brute force optimization, enumerate all policies and find the best policy. Enumerating all policies is going to get progressively harder as time increases. Okay. So I want to go back to this basic result that I had, that in this static problem, I had a similar issue. Okay. The complexity growth was not that much, but there was still a complexity growth, and I could go from this exponential dependence to a linear dependence. And I want to see if it is possible to go from this exponential over time dependence to a complexity which is linear over time. Okay. It will turn out that I cannot always get linear dependence over time. I'll have to make certain assumptions on my model under which I'll get linear complexity, but we can definitely get something which is simpler than this brute force search complexity. Okay. So how should we proceed? So what has fundamentally changed from what we did in this problem? Start from this. I have this procedure of folding my tree, right? I go here. If there's a decision node, I average. If there's a chance node, I average. If it's a decision node, I optimize. Can I use the same procedure here? Right? So I can do exactly the same thing. Nothing has changed. Right? These numbers are more complicated. I have to do more computations, but conceptually nothing has changed. I start at this node. So what I'm going to do is I'll start introducing some notation in parallel. I'll do some operations in this tree, and I'll write in terms of my notation what is happening. Okay. So I'm going to say there are random variables W0, which determines what happens at the beginning. In the tree that I drew here, I just said state is 0. That might not be the case. There may be some distribution over the initial state. All that thing is captured by what happens before the system starts running. And then I'll assume there are some random variables W1, W2 till W capital T, which determine what are the disturbance or chance moves that happen in the problem at every time. Okay? Whatever randomness happens at time t gets clubbed in Wt. Okay? I am going to use this notation, and we'll overload this notation later in the course, but I am going to say Ht is the history of what has happened so far. Okay. So remember, when I was looking at this model, I said I can talk about this node in terms of index that by the value of f. I can index this node with the value of fa, and so on. And that's exactly what I'm doing. If I want to talk about this node, rather than explicitly writing f1, a1, f2, a2, or f1, a1, w1, a2, I'm just going to write it as ht. Okay. So our assumption is this ht is going to be, in general, in this case, the values of w from 0 to t, values of actions from 1 to t minus 1. This is everything which has happened in the system in the past. What did chance do when it was, what did nature do when it was its turn to move? What did the decision maker do when it was his turn to move? And I'm looking at the decision nodes. So everything that has happened before that are the realizations of this variable. Okay. I'm capturing that in W0. So I'm not doing a state space model, so I'm just working on trajectories for now. Okay. So the final assumption that I'll make is at the end of t steps, there is an outcome. This outcome in this case is going to be what was ht, what action did the decision maker take here, and what action did nature take at the terminal time. Okay. So this is h capital T if my system is running for time capital T. What the decision maker does and what nature does gives me an outcome. Okay. And I'll assume there is a cost function, capital C, which looks at the outcome, and this is the cost that the system incurs. So my general model is that I have some what we will call primitive random variables. These capture all the uncertainty that happens in the system. Some of this uncertainty happens before the decision maker takes its first decision. Other uncertainty happens at each time after the decision maker makes a decision. Okay? There is nothing else random in the system. Everything is captured here. And I need a joint distribution on all these random variables. I'm making no other assumption. They don't need to be independent or anything. It's just I have a joint distribution of all of them. I have to choose these ATs. And the basic assumption is that in general, A of t can be some function of everything that has happened so far. So I'm going to assume that my decision maker observes everything in the past. It has no uncertainty about what happened in the past, but it does not know what will happen in the future. It must, on day 1, it must act without knowing what is the realization of the demand on day 1. On day 2, it knows what was the realization of demand on day 1, but it does not know what is the realization of demand on day 2, and so on. Okay? So, yeah. No, this is t minus 1. Yes, HT is this decision node, so it does not include AT.
No, but it includes everything up to now, not just the past.
Everything up to now. So by past, I mean the entire past. Everything from time 0 to now is what I'm calling past. So I have this optimization problem. So what I want to do is I'll call pi to be equal to collection of the policy at time 1, policy at time 2, till the policy at time t to be the overall policy of the system. And I want to say j of pi is going to be the expectation under this policy pi of the cost of the outcome. And this notation means that whenever so you see, I have this system where I'm giving you a joint distribution on whatever happens at the nodes where nature acts. And through the policy, I tell you what branch will be chosen at the nodes when the decision maker is acting. So if I give you both of them, I have a distribution on all the outcomes. I can use basic laws of probability to compute that, and therefore I can compute this expectation. So the optimization problem I'm interested in is look at every policy. For every policy, do this computation, find the policy which has the best performance. Yeah.
For clarification, sir, is AT determined after observing WT?
No, in my model, this is before WT.
But HT then should not have WT. Should have been.
Yes, thank you. Yeah, this is WT minus 1. Yes, thank you. Yes. I'll get to state. I'm not looking at state at all. So I just have something where decision agent acts, nature acts, agent acts, nature acts, and I know the past values of what has happened in the past. This is the cumulative cost at the end. So there is no decomposition. This is the simplest instance of a multi-stage decision problem. Okay? Because I don't want to add any features which were not present in my simple one-step problem. Okay? And now I know how to solve this problem, right? I know I'm going to look at this. So this was our intuition, right? I look at the last node, last layer. This is chance. So I average according to this, right? What does it mean to average these variables? This is, I'm going to compute Q terminal time for any history at that time and any action at that time. I'll compute the expectation of the terminal cost, which depends on the history at that time, the action at that time, and WT, conditioned on HT is little ht and AT is little at. Okay? This is the expectation that I do. I look at what are the numbers of these probabilities. These numbers can be a function of the trajectory so far, right? So that expression captures all of that. Okay. Once I do this, in this two-stage problem, this last layer is no longer there. I am now at the decision node. And what do I do at the decision node? I look at a particular history. I see what is the value that I'll get for every action, which is given by that Q function, and I compute the action with the smallest value. So as before, I'm going to call this Q star, and then I'm going to do V star of capital T of HT is minimize Q star of T of HT and AT over all values of AT. Okay. And I'll also remember what was the action that I took in these cases, and I'll pick any one of the arguments at this step. Okay. So what I'm saying now is, when I remove this last layer and I'm at this decision node, I look at for every action what's the value that I get, and I take the smaller value. And I keep track of the branch which was giving me the smaller value. So once I have done this procedure, what I'll be left with is I have state 1, then W1, and then these things, and I have a value for, this is now V2 star of H2, this is V2 star of a different H2, these H21, H22, these are different histories, right? So for each one of these, I have now computed a value at that node, which is the cost to go if my system was starting at this node of the tree and I had taken optimal actions in the future. Okay. Now I'm exactly in a one-stage problem, and I follow this procedure again. I do averaging over the last nodes, I do optimization over the decision nodes. Okay. So what that's going to look like? So that was my initialization step, and now I just have to repeat it for all times in the going backwards here. So I say for everything till the last step going backwards, I'll keep on computing Q star of T of HT and AT is going to be the expectation and phi star T is going to be an argmin of the same thing. Okay. So I have a basic recursive procedure for computing a policy. I haven't shown this policy is optimal. My claim is this policy is optimal. We'll see in a bit why this policy is optimal, but sort of in some sense, intuitively from this example, we know that what I'm really saying is, if I was at time 2 and I told you, look, in the past something has happened. I don't care what happened in the past. I am at this node. What decision should I take? I don't care what happened in the past that brought me here. Now that I'm at this history, I have to take an action to optimize what will happen in the future. So this is what I'm doing at the last node. Once I've done it at the last node and I'm at this node, I'm saying, look, I'm somewhere. I don't know what happened in the past that brought me here. I have to act now, and I know from the next time onwards, I'm playing optimally. And I'm playing optimally means that my value is some number which I have computed. And if I'm doing optimally from this next point onwards, what action should I take? I don't care how I reached here. I should take an action which optimizes this one-step thing. Okay. So what I have now done is I've gone from a optimization problem over policies to a recursive optimization problem over actions. At every history, I have to solve that I'm making here is that my decision maker knows everything that has happened in the system. Okay? We'll get to later what happens if my decision maker did not observe everything. Okay? I think the difficulty for those of you who have seen MDPs before, I think the difficulty is if you start with a MDP model, partial observation seems like this scary thing. But I mean, this is all some very basic first principles thing, and now it will become, when we go to partial observation, it will become very straightforward to think about partially observed models.
So at present you don't have Apollonians here?
I have no assumptions. I'll get to, towards the end of this lecture, I'll get to MDP models on what are the sequence of assumptions that I need to make to go from this model to an MDP model. Because I can compute that as a function of all the previous things. Okay? In my dynamics, S is just a bookkeeping variable. Okay? We'll come later why we can get to S and so on, but if I tell you the history of the demand realizations and actions that had happened in the past, you can recompute S. Yeah? No. I am right now saying it can be arbitrary. And that's the reason I have to always talk about conditional distributions here, right? So you know what will happen, there are some W's which are part of this history, and there are some W's in the future, and I'll have to do that conditional computation, right? So this is going to be computationally horrendous. If I make some assumptions, I can simplify those things, and I'll explain which assumptions I want to make, right? But the key point I want to say is, this is the most general problem that I can have for a finite state, fully observed system. All I'm saying is, I have a stochastic system, right? So let me rewrite this. The model is this. I have a stochastic system, and this is a system in which I give an observation WT, sorry, give an input WT, which is a stochastic input, and I give a control input AT at every time. And I have a decision maker, which can, I'm sort of really saying that the output of this is you get to observe WT and AT. I have a decision maker or an agent which observes these things. There is a delay here somewhere, and then it chooses the controlled input of my system. And nature is generating this sequence of random variables, so a stochastic process in general, which is controlling the stochastic input of my system. The system runs for some time, and I get a cost which depends on the outcome of the system. Okay? So what we do in sort of systems theory, if I have an input-output model, I'll try to construct a state space model which is equivalent we normally see in MDPs. All right. So why is this policy optimal? Exactly the same proof as last time works. What was my previous proof? What happens if I specify a policy rather than the optimal policy? Then at all these decision nodes, I'm telling you what to do. So I can do the following policy evaluation dynamic program, where I initialize q pi of t in the same way. But when it gets to the value function computation, rather than doing optimization, I'm going to take the Q function and evaluate it at the policy. Okay. And once I go to this step, I'll go to then the recursive step, I would be computing q pi t of ht at to do the expectation of the value function at the next time ht, at, and wt. Conditioned on ht equals to ht, wt equals, sorry, at equals to at, and v pi t of ht is equal to q pi t of ht pi t of ht. Okay. So, the same algorithm, if I tell you what you are doing at all of the decision nodes, I can use the same algorithm to evaluate the performance of a policy. Okay. And the proof of optimality in the static case was I showed that q stars were lower envelopes of q pi for every pi, and then I showed that if the policy was actually pi star, this was equal, right. That same argument is true here as well. So, my proof is just going to be a backward induction proof, which says q star of t is less than equal to q pi of t, and I mean this pointwise, while q and this will imply that v pi star of t, so recursively I will show this for all t, is less than, is equal to v star of t is less than equal to v pi of t for all pi. Okay. So, you recursively show these things in a backward induction manner. At time capital T, this statement is true by construction, this is true by definition of the minimizer, and I recursively show that if this guy was a lower envelope of v pi, then this guy will be a lower envelope of v pi also. So, by taking this view of just thinking of the decision problem in terms of everything that I have seen in the system, how should I act? I get a very, very simple algorithm, very, very simple proof of why this thing is optimal, with the caveat that since I have made no assumptions on my model, in general this is going to be a complicated, a difficult problem to solve, because the number of nodes in my tree are increasing quite a lot. So, all the efforts that we are going to spend in rest of the course is trying to understand, can I reduce this computational effort? Okay. So, I can make conditions under which I will have an exact simplification that I can, what we did in the static case, right. We said if I can identify information that is irrelevant, I can throw away that information. That means I can reduce the number of decision assumptions, I cannot do anything else. So, yeah. So, you see, if I have to give you a policy, I need to know how to act at each node. So, I can't do any more simplification than that. All right. So, what we are going to do now is I want to slowly add 3 assumptions which will simplify the model. So, the first assumption I will make is regarding these guys. Okay. So far I said these are just some arbitrarily distributed random variables. What happens if these are independent? Okay. So, assumption 1 is my primitive random variables are independent. Okay. So, let us go to this step. If my primitive random variables are independent, the distribution of W capital T does not depend on anything that happened in the past, right? When I go to this second step, the conditional distribution of W little t also does not depend on anything that had happened in the past. So if I have primitive random variables, my recursive step becomes Qt of Ht At is equal to the, yeah. Wt is not a part of Ht. The Ht was Wt minus 1, At minus 1. So I get expectation over, this is either star of pi, I don't care, so I'll not write anything on top, Vt plus 1 of Ht, At, Wt, and this is an expectation I can compute because Wt is an independent random variable from whatever happened here. So I just average this with respect to Wt. Okay? So in the inventory management example that I was giving, this would happen if the demand over time is independent. Okay? The demand that I have today is same as the demand that I have tomorrow. It doesn't need for it just needs to be sorry, I misspoke. The demand is independent across time. It doesn't need to be identical over time. So the demand today should be independent of the demand tomorrow. It can be a different demand tomorrow. Okay. So is this clear? So this is providing me, I don't need to use Bayes rule to compute conditional expectations to compute this guy. I can just use that from the marginal distributions of my primitive random variables. Okay. So the simplification that has happened is that in the original problem, I needed to specify the joint distribution of random variables, and when I'm doing computations, I needed to compute conditional expectations to do the computations. In this case, since everything is independent, conditional expectations are same as unconditional expectations, so I only need to store the marginal distributions of my primitive random variables. All right. Not really, because I was hiding this complexity under the rug. It would have my per step complexity, so the constant will change, but it will not change the complexity in terms of the number of nodes where I have to do this computation. Now, the second simplification that I'm going to make is what many of you have been alluding to, is to assume that I have a per step cost. Okay. So what does the per step cost do? What I'm saying is, suppose the cost which depended on the outcome at time t can be written recursively as cost which is incurred at each time, and I'm going to say that this is equal to sum of some function t equals to 1 to capital T of cost which can change over time of the history at time t, action at time t, and so I should use capital variables because I've used capital the other side, history at time t, action at time t, and possibly noise at time t. Okay. So I'm saying it is possible that the cost that I incurred was, I didn't have to wait till the end of the horizon to incur certain costs. The costs were being incurred as we went along. Okay. This leads to a subtle simplification. So what's going to happen now? My claim is the following. I'll write the dynamic program as follows. I'll start at Q capital T. It's a function of Ht and At. But what I'm thinking now is, there is certain cost that I have incurred in the past. The cost from time 1 up to time t minus 1. Okay. I cannot do anything about that cost. That cost has been incurred. This optimization problem was saying, look at all the costs in the past plus the cost that you'll incur in the future, and you evaluate that. I'm going to now do something very different. I'm going to just look at the expected value of the little c capital T of H capital T, A capital T, and W capital T. And for simplicity, I'll say that both assumptions 1 and 2 hold, just so that I don't have to write conditional expectations. Okay. So under assumptions 1 and 2, so this kind of looks the same, but here this was the cumulative cost along the trajectory, while here this is just the cost that I incur at the last time step. Okay. So this guy is going to be this guy plus the cost incurred in the past, which is just a function of ht, will give me that guy, right? So I'll call this q star with some abuse of notation, and I'm going to say v star of capital T of ht is going to be the same. I'll minimize over actions q star capital T of ht at. Okay. Now the recursive step becomes somewhat different, because now in the recursive step what I have to do is I have to say that when I look at the cost to go function at time little t, history ht and at, I know my action is going to give me some cost now, and then I'll have the cost to go from next time onwards. So this has to be defined as the expectation of the current cost that I will incur plus the cost to go from the next time onwards. And again, I'm making assumption 1 also, so I'm not writing conditional expectations. This is just unconditional expectations. Okay? And now the value function computation is the same. And I mean, I can either relate this with this guy and show the equivalence, or I can just follow the same proof as before. I compare that these guys are lower envelopes of the policy evaluation function for any one, and at the optimal policy will reach this lower envelope. Okay. So nothing changes in the overall structure. What's happening now is that these costs are incurred incrementally. So I'm incurring this cost separately. Okay? But this has big implication when I'm thinking in terms of simplification of the problem. Okay? So let me go back to the inventory management problem and say, because you see the key idea from last time was, can I figure out a way, can I figure out a compression of my observation so far such that my Q function is same for all observations, which give me the same compression, right? That's what we were saying. I have this function sigma of my observation such that if 2 states give me the same sigma, their performance is the same. In that setting, it makes a big difference whether I had the cost incurred at the end or cost incurred incrementally. Okay? So let's go back to this example. I have, starting with 0 state, I order high or low, nature decides high or low, then I order again high or low, and then nature decides high or low. Okay? And let's say my numbers are such that if I choose low followed by high, so let's say low followed by low is same as high followed by high. Okay? Suppose my numbers were such that if I ordered low amount and the demand was low, the amount of goods that I have here is the same as the amount of goods if I had ordered high and the demand was high. So let's say these were exactly the same numbers that I could do. Okay? So what will mean here is that at this stage and at this stage, I have the same amount of goods in my warehouse. Okay? I have followed different trajectories to reach here. The cost that I have incurred in the past is different, because here I ordered low amount of goods, here I ordered high amount of goods. But what is happening in the future is the same at both these cases, right? So when I look at this subtree, that is exactly same as this subtree, in the sense of the costs that I will incur in the future for every trajectory is the same in both these trees. So if I have a model which can capture this effect, right, I can figure out a compression of the history such that the futures are identical, then I can get a simplification. Okay? The simplest model which does that is a state space model. Okay? Yeah.
So here, going back to this assumption 2, if I assume that all C0, C1 up to Ct minus 1 are 0, and
Yeah.
T capital T is C,
Mhm.
then we go back to the
Yes.
so since that is special case of one, so
Yes.
it's not clear which one is.
So I'll have to add assumption 3 in order to get what I want, right? But really, I'm saying if this was truly a per step cost, which depended on the, so I'll need to have a state type of variable as well in order to get a complete simplification. Okay? Yeah. Yes, that's. I mean, I can have a cost which has something like that, right? If I'm just looking at the last realization or something, that's a special case of the entire history. I'm saying even if I had a generic cost which depended on everything that has happened so far, I can handle that in dynamic programming.
Argument of Ct is capital OT, right? That tuple is capital.
In here, it was capital OT for the terminal cost thing.
Even here.
Here, it's effectively capital OT, yes. Yeah. Okay. So my third model, third assumption is going to be a state space model. So how many people have seen a reduction from an input-output model to a state space model? So maybe like a course in linear systems, or a course in nonlinear systems, or a course in automata theory. And how many have seen Markov chains in a course in probability? Okay. So Markov chains is one instance of a state space model for stochastic processes. Okay. What happens in state space models is, suppose the following happens, right? What is the case in the inventory management problem that I gave? That there is some process St which lies in some set S such that the following is true. The state at time t plus 1 is some function of the state at time t, the action at time t, and the disturbance at time t. In the inventory management example, Ft plus 1 was equal to Ft plus At minus Wt. Okay. In addition, my per step cost, so I'm assuming that the total cost as a function of the outcome can be decomposed into a cumulative cost which depends on Ct of Ft, At, and Wt. Okay. So if I have a state space model and that state is sufficient for capturing the per step cost, and because my decision maker observes A and W, the decision maker also observes Ft. Okay. So now I have a problem which I can abstractly say, going back to this case of the news vendor problem where he was observing whether to get out from the left side of the bed or the right side of the bed, I can say at time t, my decision maker has access to Ft and Ht. In my view, I need both of these for f to be called a state. It should be state sufficient for tracking of the cost. So what happens is I can add state to the stuff of things I know, right? Because state is just a recursive computation of these things. So in principle now, I could write down Q capital T star of S capital T, H capital T, and A capital T to be the expected value of C capital T of S capital T, A capital T, and WT. I am making both three assumptions together. So my assumptions are cumulative. It's not only A3. I'm assuming primitive random variables are independent. I have a per step cost where the decomposition is in terms of state, and state evolves in a recursive manner. Okay? So I'll get this as my terminal thing. Value functions will always be ft and ht, will be minimizations over at of q capital T star of ft, ht, and at. And same thing for t in t minus 1 to 1, I'll have q star t of ft, ht, at to be expectation of ct of ft, at, wt. And this is where now things become interesting. Vt plus 1 star of, I'm going to write the ft component of this to be ft, at, wt, and the next history, which is ht, at, wt. Okay? Now my claim is the following. I can argue recursively I want to argue that without loss of optimality, I can choose at simply to be a function of ft. Okay? I'm going to explain the implications of this result first, and then we'll see how we can prove this result. Versus history, right? So far I had that it had to be a function of history. Okay? So if I have independent primitive random variables, per step costs, cumulative per step cost, and a state space model, then there is no loss of optimality in choosing an action just as a function of the current state. Okay? This can be seen as a tautology, that I have a state only if the state captures everything about the past that is relevant for the future. So if this was not a function of state, then I do not have a state. But we are going to give a proof which is sort of more structured than just kind of appealing to the definition of state. But let's see what this means. I could, right? So the simplification would really, really happen if this set was not changing over time. Yeah, this set had, or this set had a cardinality which was significantly less than the cardinality of histories. Yeah.
Is it necessary to assume independence of primitive random?
Yes.
What if I say that W is function of HT and AT?
Okay.
Or WT, sorry, ST and AT. Or I could say that WT is independent of HT given ST and AT. So I could make those primitive function of current state and action. And still
That would work. That would work. So it can be there. But so it's a modeling question, right? Because the way I'm modeling things is I'm saying I'm looking at a stochastic problem. So there must be an underlying probability space in which I'm talking about the optimization problem. There must be certain quantities which are random variables on that probability space. These are all my primitive random variables. The view that you are taking, and I'll come to that in a bit, is I could have started in terms of conditional measures and it will give a consistent representation of things as well. But pedagogically, I think it is much nicer to start with random variables on a probability space because proofs are much, much simpler. Yeah. Mm-hmm. It can change over time, yes. Yeah. So it could be, for example, it is like this at certain time, and it is maybe a multiplied by w at some other time. As I'm making an assumption, I know these functions before the system starts running. Every randomness, this is a deterministic function. Whatever is random is captured in WT. Okay. Yes, precisely, right? So what I have here is ST is some compression of the history. Okay? And so kind of, if I want to give a proof, I would have to show that if I take two states, if S1, how do I say that? If H1t and H2t give me the same state, then I should have Q1 star of H1t. If I was just doing the original problem, this should have been the case. Right? So this is a compression of the history such that my Q functions will be equal, and that's going to be my proof methodology. Okay? Before that, I want to say, if I have this, what is the simplification that I get? So now is the case when my dynamic program really, really simplifies, because what happens is I don't keep track of H here. I don't keep track of H here, I don't keep track of H here, and I don't keep track of H here. So my simplified dynamic program is Q capital T star of ST and AT is expectation of C capital T of ST, AT, WT, V star T of ST is minimization of Q star T of ST and AT, and V star T of ST will be the minimization of this. Okay? So what has happened now is that I have to, at every time, I have to keep track of script of S times script of A number of computations. Right? That's the size of my Q table. And I have to do this for every time. So under these assumptions, I have an algorithm whose complexity is linear in time. Okay? Because I got rid of the histories. Yeah. I don't believe so. So what you're saying is, if the function here depended on the entire history rather than the current state, what will happen is I need to have that history here in order to compute that expectation. So if I have that history here, I cannot throw it from the left-hand side. Right? So you see, the reason why this thing works is, and this is the nature of the proof, this is the argument that I have to prove, but I cannot prove it at any arbitrary time. If I'm keeping track of the history in the future, I cannot throw away the history now. Okay? So sort of the way my proof is going to work is I look at the terminal time step and I look at this problem and I want to say this problem can be simplified to this problem. Okay? I can do that by invoking Blackwell's principle of irrelevant information. I have access to some variable ht which does not affect the distribution of Wt at all. Therefore, by Blackwell's principle, at the terminal time I can do this and this policy is optimal. Okay? Now let me go to some time and let me assume from this time onwards throwing away history was optimal. Okay? That would mean that the value function from that time onwards did not depend on this component. Okay? And if the value function at time t plus 1 onwards did not depend on this component, then I can again invoke Blackwell and say the value function at time t should also not depend on the history. Okay? So that's going to be my proof while going backwards. So this is kind of the beauty of dynamic programming. There is just one single proof idea. I prove something for the terminal time, I do that for a backward induction step, and we are done. Okay? Yeah.
Keep track of the ST is the same for both HT1 and HT2, right?
Yes, that's the, so if I have two guys, which, yes, I should say, such that sigma of h1t is sigma of h2t. Yes, in this course, I'm going to restrict myself to finite horizon. So it doesn't really make a difference. Even if the cost and the dynamics were time invariant, it would be a function of time. So in general, some of these results simplify when we are going to infinite horizon, but that would require some discussion of fixed point theorems. So in this course, we'll just look at finite horizon. Okay, questions? So this is our big result. I look at a system where dynamics are given like this, cost is like this, and I have an assumption that, which I erased, that my primitive random variables are independent. Under these three assumptions, I have a dynamic programming decomposition, which is given by this. The key benefit is that the complexity is a function of it's linear in time and linear in the size of the state and the number of actions. Okay. Now, in lot of, so this theory comes up in very, very different application areas, and in certain application areas, it is more natural to consider a slightly different model. Okay. I'm going to describe that model, and that's the model that we'll use in the approximation part, just because it is more compact to work with. But I'll argue that conceptually that model and the model we are working with are equivalent. Okay, and again, let me motivate the model by an example. So suppose I have a system which is naturally described as a Markov chain. Okay. So let's say my system had state space 0, 1, 2, minus 1, minus 2, and there is some dynamics on this. So let's say I have dynamics where it is going out with probability 3/4, or let's say going out with probability 1/2, coming back with probability 1/4, and staying in its place with probability 1/4. Okay. So I have some system where the natural tendency of the system is to drift towards either +2 or -2. Okay. I have the option of applying some control, maybe using some kind of energy in the system, and try to force the state to go towards the middle. So let's say this is the dynamics of the system if I don't do anything, and I have the option of doing something which has some cost, and when I take this action, my system starts drifting towards the middle. So the direction of these arrows just reverse. and all the others are self loops with the right numbers. So, in something like this now, let's say I have a per step cost which depended on the state and action, which is s squared. The farther I am, the system is in a worse state, and it takes me certain cost to apply this corrective action. So, the cost is lambda times a, which means there is no cost if I am running the system in its free state, while I have to pay a cost when I run the system here. Okay. So, in models like applications like queuing systems, some communication systems, where we naturally model certain components like Markov chains, it's natural to say if I apply a control action, the dynamics of the Markov chain changes in a certain way. Okay. My claim is that this model, for almost all practical purposes, this is definitely true for finite state spaces. I need some technical assumptions for continuous state spaces, but I am going to say this model is equivalent to a model in which my dynamics can be written as follows. Okay. So, this dynamical model and this controlled transition kernel model are identical. If I give you a Markov chain model like this, I can construct a function f such that these two are behaviorally the same, and if I give you that, I can construct a Markov chain possibly over a continuous alphabet such that behaviorally the systems are the same. Okay. The reason why in sort of when we are talking about computation and approximation, this type of thing is slightly useful, is that in this model I have to separately capture the distribution of W. I have to say what f is and so on, while this model I can use Markov chain terminology and Markov chain notation to capture all of those things in a more compact notation. So, I can define what is called a controlled transition matrix. So, all of you have seen Markov chains before. So, in a Markov chain, to describe this, I'll write a transition matrix, right? So, I'll say this is something like this, and this guy has now whatever 0 to 1/2, and I'll fill these up according to these numbers that are there, right? The way we are thinking about this is that in this problem now, I can think of this first Markov chain as a controlled transition matrix if I choose action equals to 0, and I describe the transition matrix of the second one as a transition matrix when the action is equal to 1. Okay. So, in the MDP model or a controlled Markov chain model, I am going to assume I am given transition matrices, one for every state. So, I am given f of a for every one for every action, I am sorry, and I am given a per step cost function which is function of state action to r. Okay. It can be a function of state action and next state, it does not really change anything, but we will stick with this just to have a slightly more compact representation. And exactly the DP that I wrote there, I can write that as, I'll sort of write it slightly differently just so that I don't have to repeat this terminal step all the time. And this is, which will simplify my proof even more. I'll say there is a value function at time t plus 1, which is identically 0, and then for time t equals to capital T to 1, I'm going to do q capital T of q t of SA is expectation of. So, you see I'm going to write this guy C t of SA plus V t plus 1 of S t plus 1 as C t of SA. This comes out of the expectation plus summation over the next state, probability of the next state given the current state and action, Vt plus 1 of Ft plus 1. So, I can write it more compactly using a Markov chain evaluation formula, and the value function remains the same as before. These should be stars. V star, this is minimization over actions, Q star of S and A. Okay. So, sort of take my word for it in terms of why this model and this model are identical. And we can use a slightly more compact notation to write our dynamic program. Okay? Oh yes, thank you. We have 1 or 2 minutes. Does anyone want to give an intuition for why I can go from a Markov chain model to something like this? So if I give you this chain, right? So I say from state 0, if I take action 0, I'm going to this guy with probability half, this guy with probability half, so there is no self loop here. Can I construct a function f which will do that? It's much, much simpler than that. I'll just say take a uniform random variable, and from a uniform random variable, I can generate any PMF, right? So in the discrete case, it is trivial to do that by taking W's to be all uniform. Okay? If I'm in continuous state spaces, I need a bit more thing, but it's straightforward that I can go from here to here. The reverse, right? I just say what is the probability of all the W's which will take me from 0 to 1, right? And I write that number in the corresponding thing of the matrix, right? So it's easy to see in the finite case why I can go back and forth between these two representations. Okay? And as I said, in the rest of the course, we'll stick with this representation because it's just slightly easier to write the computational part with this. But I want you to remember this entire construction. So what we'll do is we'll talk about certain properties of value functions in next lecture, talk about certain approximation ideas later on, and then I want to come back to the tree representation and say what happens to the partial observations. Okay? And the key takeaway is if we can understand approximation for fully observed models, approximation for partially observed models is going to be trivial if we have this point of view. All right. Sorry? Huffman, no, but Viterbi decoding is exactly, Viterbi is exactly this. Yeah, so Viterbi is exactly this. Huffman coding, in principle, I guess, yes.
I want an easy proof of optimality of Hoffman. This is why I can lift some.
Huffman, I mean, you don't like the